Before stars existed, before galaxies formed, before space had shape or direction, the universe was not yet a place. There were no distances to cross, no light to travel, no clocks to measure passing moments. Everything we see today, every atom, every horizon, every law that governs motion and matter, traces its history back to a single early state, where the universe was unimaginably hot, dense, and compact. This beginning is known as the Big Bang. Not an explosion in space, but the expansion of space itself. A transition from an early condition so extreme that our familiar ideas of size, temperature, and even time begin to lose their meaning. From this starting point, the universe cooled and expanded, giving rise to particles, forces, atoms, stars, and eventually the vast cosmic structures that stretch across billions of light-years. Modern cosmology has become remarkably successful at describing this unfolding story. Observations of distant galaxies show that space is still expanding. Ancient light, released when the universe was young, fills the cosmos as a faint microwave glow. The simplest elements formed in precise ratios that match predictions made decades before they were measured. Together, these discoveries allow scientists to reconstruct the universe's history back to a fraction of a second after expansion began. Yet embedded within this success is a deeper and more unsettling question. If the Big Bang marks the beginning of everything we can observe, what brought it about? If space and time themselves emerged from that early state, what does it even mean to ask what happened before? Was there a cause, a prior condition, or a deeper framework from which the universe emerged? Or is the Big Bang not a beginning at all, but a boundary beyond which our current understanding cannot pass? These questions sit at the edge of science, where mathematics, observation, and theory begin to thin out. They are not questions of belief or speculation alone, but consequences of taking our best physical theories seriously and following them as far back as they will go. When we do, we discover that the universe's origin is not just a mystery of distance or age, but a challenge to the very ideas of cause, sequence, and explanation. To explore what might have created the Big Bang, we must first understand what the Big Bang truly represents, what it explains with extraordinary precision, and where its explanatory power ends. Only then can we examine the ideas physicists have proposed to reach beyond it, and why the answer, if there is one, may lie outside the universe as we experience it at all. To understand why this question is so difficult, it helps to separate two ideas that are often blended together. One is the origin of the universe as a physical system. The other is the origin of existence itself. The Big Bang theory speaks only to the first. It describes how the universe evolved from an early, extremely hot and dense state into the structured cosmos we observe today. It does not claim to explain why that state existed, nor whether it was truly the first moment of reality. When cosmologists trace the expansion of the universe backward using the equations of general relativity, they find that distances shrink, temperatures rise, and densities increase. Eventually, the mathematics points toward a limit where these quantities become infinite. This boundary is often described as the beginning of time, but it is better understood as the point where our current physical theories stop working. At that scale, gravity behaves in ways that classical equations cannot describe, and quantum effects become unavoidable. This breakdown does not necessarily mean the universe sprang into being from nothing. It means only that the tools used to describe it no longer apply. Just as the equations of fluid motion fail when describing individual molecules, the equations of spacetime fail when pushed to the smallest possible scales. The apparent beginning revealed by the mathematics may be less like a true origin and more like the edge of a map, beyond which the terrain has not yet been charted. Because of this, The question of what created the Big Bang is not dismissed by physicists. Instead, it is transformed. Rather than asking what event happened before the universe began, researchers ask what deeper laws or structures could give rise to an expanding universe at all. Some ideas suggest earlier phases of reality. Others suggest repeating cycles. And some suggest that the question itself assumes concepts, like time and causality, that may not apply at the deepest level. At this boundary between what can be tested and what can only be inferred, cosmology becomes less about answers and more about limits. The closer we move toward the origin, the more the universe resists familiar explanations, inviting a different way of thinking about beginnings, causes, and the nature of existence itself. One of the most important ideas to grasp is that time itself appears to be part of what the Big Bang describes. In everyday experience, time feels absolute. Moments follow one another in a steady sequence, and causes always come before effects. But in modern physics, time is not a universal backdrop. It is woven together with space into a single fabric known as spacetime. This fabric can stretch, bend, and evolve. When scientists run the equations of general relativity backward toward the earliest moments of the universe, they do not find time ticking away into an earlier and earlier past. Instead, they find time behaving strangely, slowing down, losing definition, and eventually reaching a point where the concept of earlier no longer has a clear meaning. In this view, the Big Bang is not something that happened at a moment in time. It is the point at which time itself begins to be a meaningful concept. This creates a profound shift in how the origin question is framed. If time emerged with the expansion of the universe, then asking what happened before the Big Bang may be like asking what lies north of the North Pole. The question assumes a direction that no longer exists beyond a certain boundary. There may be no earlier moments in the way we normally understand them. Still, this does not close the door on deeper explanations. Instead, it suggests that any cause of the Big Bang, if such a cause exists, would not operate within time as we experience it. It would belong to a more fundamental description of reality, one in which space and time themselves are emergent features rather than basic ingredients. To explore these ideas, physicists turn to the earliest stages of the universe that can still be described using known principles, even if only approximately. In the tiniest fractions of a second after expansion began, the universe was filled with extreme energy. Matter did not yet exist in its familiar forms. Forces that are separate today may have been unified. Quantum effects were not confined to the microscopic world, but influenced the structure of spacetime itself. This is where the question of origins begins to intersect with quantum physics. At very small scales, quantum theory allows for fluctuations. Energy can briefly appear and disappear. Fields can shift between different states. In ordinary conditions, these effects are tiny and fleeting. But at the beginning of the universe, when everything was compressed into an unimaginably small volume, such fluctuations may have played a decisive role. Some physicists propose that the Big Bang emerged from a quantum process, not as an event triggered by a classical cause, but as a transition allowed by the fundamental rules of nature. In these models, the universe may have arisen from a quantum vacuum, not a state of nothingness, but a lowest energy condition governed by physical laws. Even an empty vacuum in this sense is active, structured, and capable of change. Others take a different approach, suggesting that the Big Bang was not the first act, but a transformation. In these scenarios, the universe existed in some form before expansion began, perhaps contracting, perhaps oscillating through cycles, or perhaps existing in a state radically different from anything we can directly observe today. The Big Bang then marks a boundary between phases, rather than an absolute beginning. What unites these ideas is a recognition that the origin of the universe may not resemble familiar creation stories or mechanical causes. Instead, it may reflect deep principles about how reality behaves when pushed to its limits, where space, time, and energy lose their everyday meanings, and new descriptions are required. Among the ideas that attempt to describe these earliest moments, one concept appears repeatedly because of how effectively it explains what we observe today. This idea is known as cosmic inflation. Inflation proposes that in the earliest fraction of a second after expansion began, the universe underwent a period of extraordinarily rapid growth. Space itself expanded at a rate far greater than it does now, stretching tiny regions to enormous scales in an instant. Inflation was not introduced to answer where the universe came from. It was proposed to solve specific puzzles. When scientists studied the large-scale structure of the cosmos, they found that the universe looks remarkably uniform in all directions. Regions separated by vast distances have nearly the same temperature and physical properties, even though, under normal expansion, they would never have had time to influence one another. Inflation offers a natural explanation. It suggests that these regions were once extremely close together and part of a single, uniform patch before rapid expansion carried them far apart. Inflation also helps explain why the geometry of space appears so close to flat. Without inflation, even tiny deviations from perfect balance in the early universe would have grown dramatically over billions of years. Instead, space today appears finely balanced, as though initial irregularities were smoothed away. Rapid expansion provides a mechanism for that smoothing, stretching any curvature until it becomes nearly imperceptible across observable scales. Perhaps most importantly, inflation offers an explanation for the origin of cosmic structure. Quantum fluctuations, which are normally confined to the smallest scales, would have been stretched during inflation into macroscopic variations in density. These subtle differences became the seeds of galaxies and clusters, eventually shaping the cosmic web that fills the universe today. Observations of ancient radiation support this picture, showing faint imprints of these early fluctuations frozen into the structure of space. Yet inflation raises as many questions as it answers. While it describes how the early universe behaved, it does not fully explain why inflation began, what mechanism drove it, or how it ended. In many models, inflation is powered by a field whose properties remain unknown. The nature of this field, its origin, and its relationship to other forces remain subjects of active research. Some versions of inflation go even further, suggesting that the process may not have happened only once. In these models, inflation is eternal. While inflation ends in some regions, giving rise to universes like ours, it continues elsewhere, constantly producing new, expanding regions. Each region may have different physical properties, governed by different conditions. In this view, our universe is one outcome among many, emerging from a much larger process that has no clear beginning or end. This idea, often associated with the multiverse, is deeply controversial, not because it contradicts known physics, but because it challenges the limits of what science can test. If other regions are forever beyond observation, their existence may never be directly confirmed. Still, the idea arises naturally from attempts to extend inflationary theory, making it difficult to dismiss entirely. Other models approach the problem from a different direction. Instead of a universe that begins with expansion, they propose a universe that cycles. In these scenarios, the Big Bang is not the first moment, but a transition from a previous phase. The universe may have existed in a state of contraction before rebounding into expansion. Over immense spans of time, it could undergo repeated cycles of growth and collapse. Such models avoid the need for a singular beginning, replacing it with an eternal sequence of transformations. They also offer potential explanations for why the universe appears so large and old. However, they face significant challenges. Maintaining stability across cycles, preventing the accumulation of entropy, and matching precise observational data are all difficult problems that remain unsolved. A related class of ideas suggests that the universe emerged from a more timeless quantum state. In these descriptions, spacetime itself is not fundamental. Instead, it arises from deeper quantum relationships. The Big Bang then marks the moment when classical space and time crystallized out of a more abstract underlying reality. Before that transition, there may have been no space to expand and no time to pass, only probabilistic structures governed by quantum rules. These approaches share a common theme. They replace the image of creation as an event with the idea of emergence. The universe is not switched on like a machine, but unfolds from deeper principles that do not resemble everyday causes. In this sense, asking what created the Big Bang may be less about identifying a trigger and more about understanding the framework that allows a universe to exist at all. As physicists push their theories toward these extremes, they encounter a recurring boundary. Equations that work beautifully elsewhere begin to lose precision. Concepts that feel intuitive, such as before, after, cause, and effect, become ambiguous. The closer we approach the origin, the more the universe seems to resist simple explanation, revealing not a clear answer, but a horizon of understanding that continues to recede as knowledge advances. At this horizon of understanding, the role of quantum physics becomes unavoidable. Unlike classical physics, which describes smooth, continuous change, quantum theory is built around probabilities, fluctuations, and uncertainty. At very small scales, particles do not behave like solid objects following precise paths. Instead, they exist as waves of possibility, described by likelihood rather than certainty. When applied to the early universe, this radically changes how beginnings are understood. In quantum theory, even what appears to be empty space is not truly empty. A quantum vacuum is not nothingness. It is the lowest energy state of a field, filled with restless activity. Fields fluctuate. Energy briefly appears and disappears. Pairs of particles can momentarily emerge before vanishing again. Under ordinary conditions, these effects are fleeting and tightly constrained. But when gravity is added to the picture, especially under extreme conditions, their consequences may be far more dramatic. Some physicists propose that the Big Bang arose from such a quantum vacuum state. In these models, the universe did not need a classical cause. Instead, its emergence was a quantum transition, allowed by the fundamental rules of nature. Much like radioactive decay, which has no specific triggering event yet follows precise statistical laws, the universe may have originated as a spontaneous fluctuation that became irreversible once crowd. Expansion began. In this view, asking what caused the Big Bang may be similar to asking what caused a particular atom to decay at a particular moment. There is no hidden mechanism pushing it into action. The event simply occurs within the constraints of probability. The laws describe what is allowed, not what must happen at a specific time. The universe exists because, under certain conditions, its existence was permitted. Other quantum-inspired models take a slightly different approach. Instead of a universe appearing from a vacuum, they describe a prior state where space-time itself was governed by quantum rules. In these scenarios, geometry is not fixed. Distances and durations fluctuate. Classical space-time emerges only when the universe cools and expands enough for quantum effects to average out. The Big Bang then represents a phase transition, not from nothing to something, but from a quantum regime to a classical one. These ideas attempt to bridge the deepest gap in modern physics, the divide between general relativity and quantum mechanics. General relativity describes gravity and spacetime on large scales with extraordinary accuracy. Quantum mechanics governs particles and forces on the smallest scales with equal success. Yet when both are applied simultaneously, such as at the universe's origin, they conflict. A complete theory of quantum gravity remains elusive. Proposals such as loop quantum gravity and string theory aim to resolve this conflict. Loop quantum gravity suggests that spacetime itself is made of discrete units, preventing infinite densities and replacing the classical singularity with a bounce. String theory proposes that fundamental particles are not point-like, but tiny vibrating strings existing in higher dimensional spaces. In some versions, these extra dimensions and extended structures naturally give rise to cosmological scenarios where the Big Bang is not an absolute beginning. What makes these ideas compelling is not that they provide final answers, but that they offer consistent ways to think beyond the limits of current models. They show that the question of origins may not have a single solution, but a family of possibilities shaped by deeper laws we are only beginning to glimpse. Despite this progress, a striking feature remains. All of these explanations rely on laws of physics. Equations still govern behavior. Principles still constrain outcomes. Even a universe that arises spontaneously from a quantum process does so according to rules. This leads to an even deeper question, one that physics alone may never fully resolve. Why do these laws exist at all? And why do they permit a universe capable of expanding, cooling, and forming complexity? Some scientists argue that this question lies outside the domain of testable science. Others suggest that future theories may explain the laws themselves as inevitable consequences of mathematical consistency. And some propose that, in a multiverse, all possible laws exist, with our universe simply being one in which the conditions allow observers to arise. At this stage, certainty gives way to humility. The further back we trace the universe, the more we encounter limits not only in measurement, but in explanation. The Big Bang may mark the beginning of time, a transition from a prior phase, or an emergent outcome of quantum structure. Each possibility is grounded in serious theoretical work, yet none can be confirmed with absolute confidence. What remains clear is that the question of what created the Big Bang reshapes how we think about beginnings. It suggests that the universe may not have started in the way stories begin, with a first moment followed by a sequence of events. Instead, it may have emerged from conditions where time, cause, and sequence themselves were not yet defined, leaving us with a universe that can be described back to a boundary, but not beyond it. As this boundary comes into focus, an important shift occurs in how cosmologists interpret the origin question. The Big Bang is no longer treated as a single moment that demands a prior cause in the usual sense. Instead, it becomes a surface of transition, a limit beyond which familiar explanations dissolve. The universe can be traced backward with extraordinary precision, yet at a certain point, the trail ends not because something definite happened, but because the concepts used to describe happenings cease to apply. This is deeply counterintuitive. Human reasoning is shaped by everyday experience, where events unfold in time and causes precede effects. But the universe at its earliest stages does not conform to this pattern. When space and time themselves are dynamic and emergent, causality may not operate as a simple chain. What appears to us as a beginning may instead be the lowest point of description, the simplest state from which complexity unfolds. In this sense, the Big Bang can be understood less as an origin and more as a boundary condition. It marks the point where the universe becomes describable in terms of expanding space, cooling matter, and evolving structure. What lies beyond that boundary may not be another chapter in the same story, but a different kind of narrative altogether, written in a language physics has not yet learned to speak fluently. Some researchers suggest that this boundary is not absolute. As theories of quantum gravity develop, the sharp edge of the Big Bang may soften. What once appeared as a singular beginning could be revealed as a smooth transition, governed by rules that prevent infinities and replace them with finite, well-behaved quantities. In these views, the universe never reaches a state of infinite density or temperature. Instead, it passes through an extreme but finite phase that reshapes spacetime without destroying it. If this is the case, then the question of creation becomes even subtler. Rather than asking what caused the universe to appear, the focus shifts to understanding why the universe evolves at all. Why does reality permit change, expansion, and the emergence of structure? Why does it not remain frozen in some static configuration? These are questions that blend physics with deeper considerations about the nature of existence. There is also the possibility that the universe has no unique beginning. In some theoretical frameworks, time extends infinitely in both directions. The Big Bang then represents a local feature, a dramatic event within an ongoing process rather than the start of everything. From within such a universe, it would still appear as a beginning, because no information from earlier phases could cross the boundary into the expanding region we inhabit. This perspective highlights a recurring theme in cosmology. Observers are always limited by horizons. There are distances beyond which light has not yet reached us. There are energies beyond which experiments cannot probe. And there may be epochs beyond which explanation cannot penetrate. The Big Bang may be one such horizon, not because nothing exists beyond it, but because whatever does exist lies outside the reach of current understanding. Despite these limitations, the pursuit of these questions continues to shape modern physics. Each attempt to explain the Big Bang's origin forces theories to confront their deepest assumptions. What is space made of? What is time? Are the laws of physics fixed or emergent? Are they unique or one possibility among many? Even without definitive answers, the process of asking refines our understanding of what a universe is and what it means for one to exist. In the end, the question of what created the Big Bang may not yield a single, final explanation. It may instead reveal that beginnings are not always events, causes are not always temporal, and origins are not always accessible from within the systems they produce. The universe can be traced back to a state of extraordinary simplicity and density, but beyond that point, explanation gives way to possibility. The story told by modern cosmology is therefore incomplete by design. It reaches as far as evidence and theory allow, then stops at a boundary that invites further thought rather than closure. The Big Bang stands not only as the beginning of cosmic history, but as a reminder that some questions endure not because they lack answers, but because they illuminate the limits of how answers can be formed at all. This unresolved boundary has an important consequence. It means that the origin of the universe may never be reconstructed in the same way other events are. When scientists study stars, planets, or galaxies, they rely on traces left behind, light emitted, elements formed, motions preserved. The Big Bang, by contrast, sits at the edge of traceability. There is no leftover signal from a moment before spacetime became transparent to physical description. Whatever preceded that state, if anything did not leave evidence that can travel forward in a conventional sense. This does not render the question meaningless, but it changes its character. Instead of asking for a historical account, cosmologists search for consistency. They ask whether proposed models fit with what is observed now, whether they reproduce the universe's large-scale structure, its composition, its geometry, and its statistical patterns. A theory of origins is judged not by direct confirmation, but by how naturally it leads to the universe we see. In this framework, many ideas that sound abstract are treated with practical seriousness. A universe emerging from a quantum vacuum is not evaluated as a philosophical claim, but as a mathematical one. Does the model produce stable expansion? Does it avoid infinities? Does it generate the right spectrum of fluctuations? Likewise, a cyclic universe is not accepted because it feels intuitively appealing, but because it must survive precise observational tests. What makes this difficult is that multiple very different models can reproduce the same observations. Inflationary universes, bouncing universes, emergent time models, and multiverse scenarios can all be adjusted to align with current data. This creates a situation where physics reaches a plateau. Progress becomes incremental, and certainty remains elusive. At this point, the origin question intersects with a deeper issue: whether the universe requires an explanation at all. In everyday life, unexplained events demand causes. But at the most fundamental level, it is not clear that reality must conform to this expectation. Some physicists argue that the universe may simply exist as a brute fact, a configuration that does not require further justification within the framework of physical law. Others are uncomfortable with this conclusion and continue searching for deeper principles. They hope for a future theory in which the existence of a universe becomes inevitable rather than contingent. In such a theory, the laws of physics would not be arbitrary. They would follow from internal consistency, mathematical necessity, or some deeper organizing principle that leaves no room for alternatives. Whether such a theory is possible remains unknown. History shows that physics has repeatedly uncovered deeper layers beneath what once seemed fundamental. Yet it also shows that each layer introduces new questions. The hope that one final explanation will close the chain of inquiry may itself reflect a human preference for closure, rather than a property of reality. Seen this way, the Big Bang is less a problem to be solved than a feature of our perspective. From within the universe, it appears as a beginning. From outside, if such a viewpoint even exists, it may be part of a much larger structure. The fact that we cannot step outside our universe to verify this is not a failure of science, but a reminder of the conditions under which knowledge is formed. As the universe continues to expand, the traces of its earliest moments gradually fade. Galaxies move beyond observable horizons. Ancient light stretches thinner and colder. Over immense spans of time, even the evidence we now rely on will become harder to recover. The window through which the universe can be studied is finite, both backward and forward. And yet, within that window, the story revealed is extraordinary. A universe governed by simple principles gives rise to complexity, structure, and observers capable of questioning their own origins. Whether or not the Big Bang has a cause in the traditional sense, its consequences are undeniable. From a near featureless early state emerged stars, chemistry, planets, and minds. The question of what created the Big Bang remains open not because science has failed, but because the universe has led inquiry to its natural edge. What lies beyond that edge may one day be described in new terms, or it may remain forever beyond articulation. Either way, the search itself reshapes how existence is understood, revealing that the deepest mysteries are not always those that demand answers, but those that redefine what an answer can be. From this perspective, the Big Bang becomes a mirror held up to the limits of explanation. It shows how far observation, mathematics, and theory can be pushed before the questions themselves begin to change shape. At first, the universe invites reconstruction, timelines, temperatures, densities, and processes that can be described with increasing confidence. Then, abruptly, the familiar scaffolding falls away. What replaces it is not emptiness, but uncertainty structured by law. Even the most speculative models are constrained. They must conserve energy in appropriate limits. They must respect symmetry where symmetry is observed. They must reduce to known physics when conditions allow. The freedom to imagine is narrow, bounded by consistency and evidence, even when certainty cannot be reached. This is why the origin question remains scientifically meaningful, despite its elusiveness. It acts as a stress test for ideas about reality. Any theory that claims to describe the universe at its deepest level must eventually confront it. How does spacetime arise? Why does expansion occur? Why do the laws take the form they do? Each attempt to answer one of these questions reshapes the others. There is also a quiet implication often left unstated. The universe does not appear tailored for explanation. Its earliest moments are not arranged to leave clear signatures of their cause. Instead, the universe reveals just enough to allow reconstruction up to a point, then recedes behind a conceptual horizon. This suggests that mystery is not an anomaly, but a built-in feature of cosmic inquiry. Whether future discoveries will move that horizon remains unknown. New observations, deeper theories, or entirely new frameworks may extend understanding further back than is currently possible. Or they may confirm that the boundary is fundamental, that some aspects of existence cannot be reduced to prior events or simpler terms. In either case, the Big Bang stands as more than a scientific model. It marks the place where explanation meets its limit, and where the universe shifts from something that happened to something that simply is. Beyond this point, the discussion naturally turns toward how scientists attempt to move past these limits without abandoning rigor. When direct evidence ends, progress depends on indirect constraints. The universe we observe today carries imprints of its earliest phases, not as memories of a cause, but as consequences of initial conditions. By studying those consequences in extraordinary detail, cosmologists attempt to narrow the range of what could have come before. One of the most powerful tools in this effort is precision observation. Tiny variations in ancient radiation, subtle distortions in the distribution of galaxies, and minute departures from perfect symmetry all act as clues. They do not reveal an origin directly, but they restrict what kinds of origins are possible. A universe born from violent instability would look different from one emerging smoothly from a quantum state. A universe that bounced would leave different traces than one that inflated eternally. This is why so much attention is paid to patterns rather than events. The early universe, whatever its deeper origin, imprinted structure into spacetime itself. The statistical properties of that structure are measurable. They act like fingerprints, narrowing the family of theories that remain viable. Even without seeing the cause, its effects may still be encoded in what followed. At the same time, there is growing recognition that the deepest explanation may not resemble anything we usually call a cause. In classical thinking, causes are localized. One thing happens, then another follows. But at the scale of the universe itself, locality may break down. The origin of expansion could be global rather than event-based, a property of the entire system rather than a trigger within it. Some approaches treat the universe as a self-contained solution to deeper equations. In this view, the universe does not evolve from an initial push. It exists as a complete structure, with past, present, and future woven together. The Big Bang is then not a first event, but a boundary within that structure, much like the edge of a geometric surface. Asking what caused it becomes similar to asking what caused a particular feature of a mathematical object. The question presumes an external agent where none is required. This perspective alters how explanation itself is understood. Instead of tracing chains of events backward, explanation becomes about showing that a structure is internally consistent and stable. The universe exists because it can. Its laws hold because they form a coherent system. There is no further reason in the ordinary sense, just as there is no deeper reason why a triangle has 3 sides. Whether this approach is satisfying depends as much on temperament as on physics. Some find it elegant, others find it evasive. Yet it reflects a growing awareness that the universe may not conform to expectations shaped by experience inside it. The demand for a cause may itself be a product of living in time, rather than a principle that applies to time as a whole. This brings the discussion back to time itself. If time is emergent, then causation may also be emergent. Causes may only exist once time exists. In that case, asking for a cause of the Big Bang is a category error. It applies a concept where it has no domain. The universe did not begin in time. Time began with the universe. Even so, physicists continue to explore scenarios in which time behaves differently at extreme scales. Some models allow for a form of pre-time ordering, a parameter that behaves like time but does not correspond to physical duration. Others propose that time may have existed in a different phase, with the Big Bang representing a change in its character rather than its origin. These ideas remain speculative, but they are not arbitrary. They arise from attempts to reconcile quantum mechanics with gravity and from efforts to avoid infinities that signal the breakdown of theory. Each proposal is judged by whether it preserves consistency, avoids contradiction, and aligns with what is already known. As these explorations continue, a pattern emerges. The closer physics moves toward the origin, the less it resembles narrative, and the more it resembles geometry. The universe is described not as a sequence of events, but as a structure with boundaries, transitions, and symmetries. The Big Bang sits at one such boundary, not as a spark, but as a surface. From within the universe, that surface looks like a beginning. From a more abstract perspective, it may simply be where our description changes form. The universe does not tell us what lies beyond, not because there is nothing there, but because the language used to describe what lies here no longer applies. This is why the question of what created the Big Bang persists despite decades of progress. It is not a gap waiting to be filled, but a signal that understanding has reached a conceptual edge. The universe allows itself to be known up to a point, then requires new ways of thinking that may never feel fully intuitive. Yet even at this edge, something remarkable remains. The universe is intelligible at all. From a state of extreme simplicity arose laws that can be discovered, patterns that can be measured, and structures that can support awareness. Whether or not its origin can be explained in familiar terms, the fact that it can be traced, modeled, and understood as far as it has been is itself extraordinary. As long as the universe continues to expand and reveal its structure, the question will remain open, not as a demand for an answer, but as a reminder that explanation has limits, and that those limits are as much a part of reality as the laws that operate within them. This openness is not a weakness of modern cosmology, but a defining feature of it. Unlike earlier eras where origins were often framed as singular events with definite causes, contemporary physics increasingly treats origins as questions about structure rather than moments. The universe is approached less as a story with a first page, and more as a system whose deepest properties may not admit a narrative beginning at all. One way this shift appears is in how equations are interpreted. The fundamental equations that describe spacetime do not single out a preferred starting point. They describe relationships, not origins. When these equations are applied to the universe as a whole, the Big Bang emerges not as a command written into the laws, but as a solution. It is one way, perhaps among many, but the laws can express themselves. This distinction matters. A solution is not the same as a cause. A solution exists because the underlying rules allow it, not because something external forces it into being. From this perspective, the universe may exist in the same sense that a mathematical structure exists. Not because it was created, but because it is permitted. This idea leads to a subtle reframing of the original question. Instead of asking what created the Big Bang, the focus shifts to why the laws of physics allow a universe like this to exist at all. Why do the equations admit expanding solutions? Why do they allow complexity rather than chaos or stasis? Why is there a pathway from extreme simplicity to rich structure? Some physicists argue that this pathway may be generic. Given almost any reasonable starting condition, an expanding universe may naturally evolve toward complexity. Gravity amplifies small differences. Expansion pools matter. Simple rules generate intricate outcomes. If this is the case, then the universe does not require finely tuned initial conditions. It arises robustly, not precariously. Others remain cautious. They point out that small changes in early conditions can lead to dramatically different outcomes. A slightly faster expansion could prevent galaxies from forming. A slightly stronger force could collapse everything too quickly. From this view, the universe appears balanced in a narrow range that allows structure to persist. This tension between robustness and fine balance continues to shape debates about origins. Some resolve it through selection effects. If many universes exist, observers will naturally find themselves in one where conditions permit observation. This does not explain why universes exist, but it explains why this one has the properties it does. It replaces design with consequence. Yet even this move does not eliminate the deeper mystery. A multiverse still requires a framework in which multiple universes can exist. It still depends on laws that generate them. The question of origin is not removed. It is displaced to a higher level. Throughout all of this, the Big Bang remains central, not as an answer, but as a reference point. It is the earliest moment from which reliable inference can be made. Everything after it can be traced, modeled, and compared with observation. Everything before it, if such a notion even applies, lies beyond direct reach. This division has shaped how cosmology develops. Enormous effort is invested in extracting as much information as possible from the earliest observable signals. Ancient radiation is mapped with increasing precision. The distribution of matter is measured across vast volumes. Subtle patterns are analyzed for hints of processes that occurred when the universe was still young. Each refinement narrows the field of viable theories. Some possibilities fade. Others remain stubbornly consistent with all known data. Progress is slow but not stagnant. It proceeds by exclusion rather than confirmation, by ruling out what cannot be true rather than proving what must be. At the same time, theoretical work continues to explore what lies beyond observation. New mathematical tools are developed to describe spacetime under extreme conditions. Concepts such as holography suggest that information about a volume of space may be encoded on its boundary. In some interpretations, the entire universe could be described in terms of relationships on lower dimensional surfaces. If such ideas are correct, the Big Bang may represent not a beginning within space, but a boundary of description, similar to the edge of a projection. The universe we experience could be one manifestation of a deeper, more abstract structure. In that case, Asking what created the Big Bang would be like asking what created a particular projection of a geometric object. The projection is not caused. It is derived. These ideas remain speculative, but they reflect a consistent trend. As physics advances, the universe becomes less like an event and more like a structure. Less like a thing that happened and more like a system that exists. From this vantage point, the persistence of the origin question takes on a new meaning. It is not merely a curiosity about the past. It is a probe into the foundations of explanation itself. It tests whether reality ultimately admits reasons in the way human reasoning expects. For now, the universe offers partial answers and firm limits. It allows its history to be reconstructed back to an early, dense state. It reveals patterns that suggest deep underlying order. But it does not reveal a final cause. It leaves the deepest layer open, not empty, but unresolved. And so the inquiry continues, not toward a definitive origin story, but toward a clearer understanding of what it means for a universe to exist, evolve, and be describable at all. As the discussion reaches its final stretch, the question that remains is no longer simply about beginnings, but about perspective. From within the universe, everything appears to have a history. Stars form, galaxies evolve, structures emerge, and time flows in one direction. It feels natural to assume that this chain must extend backward to a first cause. Yet the deeper physics reaches, the more that intuition is challenged. The Big Bang may represent the limit of historical explanation, not because the universe emerged from nothing, but because history itself may not extend beyond that boundary. If time is part of the universe rather than a container for it, then the universe does not sit within a larger timeline. It generates its own temporal structure as it evolves. In that case, asking what happened before the Big Bang is not an unanswered question, but an unaskable one. This does not imply that reality is arbitrary or inexplicable. It implies that explanation takes different forms at different levels. Within the universe, causes operate in time. Outside that framework, if such a notion even applies, explanation may take the form of consistency, necessity, or structure rather than sequence. One of the most striking outcomes of modern cosmology is that the universe appears comprehensible without being fully reducible. Its large-scale behavior follows simple mathematical laws, yet those laws give rise to astonishing complexity. From elementary particles emerge atoms. From atoms, chemistry. From chemistry, stars, planets, and eventually, life capable of reflection. This cascade does not require intervention at each stage. It unfolds naturally once the initial conditions and laws are in place. Whether those laws themselves require explanation remains an open question. Some physicists suspect that any sufficiently deep theory will show that the laws could not have been otherwise. Others suspect that many different laws are possible, and that we inhabit one particular realization among countless alternatives. Both views remain speculative, yet both arise naturally from attempts to push physics beyond its current boundaries. What is clear is that the Big Bang marks a transition into a universe where explanation becomes possible. Before that transition, if such a notion exists, the universe may not have been describable in terms of space, time, and matter at all. The emergence of these concepts may be inseparable from the emergence of the universe itself. In this light, the Big Bang is not merely a point in the past. It is the condition under which past and future become meaningful. It is the moment when the universe becomes a place where questions can be asked and answers can, at least partially, be found. From this perspective, the question of what created the Big Bang begins to dissolve. Not because it is trivial, but because it may be misframed. The universe may not have been created in the way objects within it are created. It may not have been assembled, triggered, or ignited. It may simply be the realization of a structure that does not require an external cause. This idea can feel unsettling. It resists the instinct to seek an origin story with a clear starting point. Yet it aligns with a recurring lesson of physics. The deepest layers of reality often defy everyday intuition. They replace familiar narratives with abstract principles that feel strange only because experience is limited to one small corner of what exists. Still, this is not the final word. Physics has surprised us before. Concepts once thought fundamental have been shown to be emergent. Boundaries once thought absolute have been crossed. It remains possible that future discoveries will reveal a deeper framework in which the Big Bang is no longer a boundary, but a feature embedded within a larger reality. For now, the universe offers no definitive answer to what created it. It offers something subtler, a coherent history from an early dense state, a set of laws that operate with remarkable consistency, and a boundary beyond which explanation gives way to possibility rather than certainty. This is where cosmology currently stands, not at the end of inquiry, but at the edge of what can be said with confidence. The Big Bang remains both a beginning and a limit, a moment that anchors our understanding while reminding us that some aspects of existence may lie forever beyond complete explanation. At that edge, the universe leaves us with a different kind of understanding. Not one that answers every question, but one that reshapes what it means to ask them. The search for what created the Big Bang begins as a scientific inquiry, but it gradually becomes an encounter with the limits of explanation itself. The closer we move toward the origin, the more the universe seems to withdraw from narrative description and present itself as a condition rather than an event. This does not diminish the achievement of modern cosmology. On the contrary, it highlights how extraordinary it is that the universe can be traced as far back as it can. From the present moment, through the formation of galaxies, stars, atoms, and particles, all the way to an early state of near uniformity and extreme density, the story holds together with remarkable coherence. Few areas of science reach so deeply into the past with such precision. And yet, that precision stops short of answering the deepest question. Not because of missing data, but because the question itself may point beyond the domain where data can exist. If space and time are features of the universe rather than containers for it, then there may be no external vantage point from which its creation can be observed or described. The universe does not sit inside a larger framework of time. It brings time into being as it evolves. Seen this way, the Big Bang is less a moment of creation and more a threshold. On one side lies a regime that can be described using the language of physics. On the other lies a realm where that language loses its meaning. The boundary is not marked by nothingness, but by silence. A place where explanation ends, not because reality disappears, but because description no longer applies. This silence has often been mistaken for emptiness. But in science, silence can be informative. It tells us where our concepts fail, where intuition breaks down, and where new ways of thinking may be required. The Big Bang occupies precisely this role. It is not merely the earliest chapter in cosmic history, but the point at which history itself begins to make sense. Whether future theories will extend understanding beyond this boundary remains unknown. It is possible that a deeper framework will emerge, revealing that what appears to be a beginning is actually a transformation within a much larger structure. It is also possible that the boundary is fundamental and that no description can reach beyond it without losing coherence. If so, the universe may not have an origin in the way questions about origin usually assume. It may not have been caused, constructed, or initiated. It may simply exist as a self-consistent reality, governed by laws that do not require justification from outside themselves. This conclusion does not close the story. It leaves it open in a quieter way. The universe becomes something that can be understood deeply without being fully explained. A reality that invites exploration, measurement, and theory, while retaining an irreducible mystery at its foundation. In the end, the question of what created the Big Bang does not lead to a single answer. It leads to a recognition that the universe is not obligated to satisfy every expectation of explanation, that some beginnings may be boundaries rather than events, and that the deepest questions in science are not always those that yield answers, but those that reveal how understanding itself is shaped. The Big Bang remains the earliest point to which the universe can be traced. Beyond it lies not a hidden mechanism or a forgotten cause, but a horizon, a limit where the universe stops offering explanations and simply is.